Hello and welcome. My name is Jelena, and today I'm going to talk about how uncertainty on the fiber span lengths influences QoT estimation using machine learning WM networks. First, I would like to acknowledge my colleagues, and if you have any questions, please send me an email. So let's start. So this is the agenda of my talk. I will start with a short introduction. Then I will talk about QoT estimation using machine learning WM networks. Then we'll explain how uncertainty on the fiber span length influences QoT estimation. And I will wrap it up with conclusion. This is a global overview of how QoT estimation of an established light path is done today and how it could be done in the future using machine learning methods. If you take a look on the left corner, today we're using an offline QoT tool for estimation, which is based on an analytical model. This analytical model can be improved using lab experiments. So with the arrival with the machine learning methods, we can go in two directions. The first one is to improve the precision of input parameters using machine learning, or we can go into the direction to completely replace QoT tool using machine learning. In that case, we need a data set. This training data set can be generated using analytical model. This can be improved by adding measurement from the lab, and this again can be improved by adding real measurement from the field using telemetry. So this should be a final grail, to take real field measurements and to generate the training data set. This is still in the research. There are a few references that you will be able to see at the end of these presentations that are studying this approach. In this study, we are using artificial neural networks for the QoT estimation. For this study, we are creating a synthetic data set for the France 43 topology, and we are generating 5 shortest light paths between each pair of nodes. So in total, we have 9,030 light paths. For each light path, we were using GN model for GeoSNR estimation, and we were including fiber nonlinearities and filtering OSNR penalties. And we were considering 33 gigabaud channel modulation formats. And in total, we had 9 modulation formats with a granularity of 25. So it means that GeoSNR was estimated it could be between 100 gigabit per second with a granularity of 25 up to 300 gigabit per second, statistic for QAM. So we considered 3 different feature selections. The first one is number of spans, the second one is number of spans and total length, and the third one is the list of span lengths. So we considered the artificial neural networks considering only one input layer, one hidden layer, and one output layer. In the hidden layer, we're considering 20 hidden neurons. For the setup details, we had 70% of data for training, 15 for validation, and 15 for testing. So the key goal of this study was to investigate how the machine learning-based QoT estimator performs depending on the different feature selections, on homogeneity of the learned light paths, and on uncertainty of their span lengths. What you see here is how our data set looks like. We were considering France topology. So on the left graph, blue one, we have the distribution of the 9,000 light paths in terms of GeoSNR. You can see that GeoSNR goes from 18 dBs to 28 dBs. Also, you can see on the right-hand side the distribution of light paths in terms of number of spans per light path. You can go from 1 span up to the light paths that has up to 33 spans. So we were running 1,000 simulations, and we were looking results in terms of 3 statistical metrics, which were used always for neural networks. The one is root mean square error. The second one is the mean absolute error. And we were looking also the maximum absolute error. So, like I said, we have 3 feature selections: number of spans for total length, and list of span lengths. You can see that the last one, the list of span lengths, has the best results in terms of the error. So this error is compared to the ground truth that we consider, which is GN model. So you can see that the list of span lengths, this feature selection gives us a root mean square error of 0.09 dBs. But then when you take a look at the maximum absolute error, it goes up to 39 dBs. This is very big absolute error. We were wondering, where does it come from? So this error comes from the estimation when we were using testing, using data set that comes from the far left or far right corner. It means that for those light paths that have the very small number of spans, or that have a high number of spans, it means that there is not enough examples in the data set while training in order to make a good estimation of the OSNR. So this is something that should be taken care of. When you're building your training data set, you should pay close attention not to make a biased data set. And not only in terms of the span length, but also to all the feature selections that you're considering. On the left graph, you can see the distribution of those errors. And like I said, the list of span lengths has the smallest error, but compared to the number of spans, they have a distribution which is spread and shows higher errors. Now we're considering how machine learning will deal with the uncertainty of the span lengths. It has been reported that 29% of the fibers in the North American network exhibit more than 5 kilometer length discrepancy between the values assumed for the network design and the actual values in the field. So we wanted to see how the machine learning will deal with this mismatch between the values in the design tool and the ones that are in the field. In order to do so, we had to produce uncertainty artificially into the training data set and into the testing data set. What you can see here on the graph, on the figure, you can see 3 curves. This graph represents root mean square error and the estimation in the function of the testing uncertainty percentage. The blue one corresponds to the 2% of training uncertainty, the red one 5%, and the yellow one the 8%. What you can see here is that, for example, for the blue one, for the 2% of training uncertainty and 2% of the testing uncertainty, you have the minimum error, which is valid for all 3 curves. So whenever you have the assumed training uncertainty, which is the same as the actual field testing uncertainty, you have the minimum error. But then when this discrepancy is getting higher, you have higher errors. So for example, if we take a look at point A on the curve yellow, which is for training of certainty of 8% and testing uncertainty of 2%, you have the root mean square error and estimation of 0.5 dB. But then if you take a look at the point B, which is for the training uncertainty of 2% and testing uncertainty of 8%, they have the same absolute difference in uncertainty between the training and testing of 6%. But the point B has higher root mean square error. What does it mean? It means that it's better to train your data with overestimating the uncertainties than to underestimating them. And in order to To generate uncertainty on our training and testing data set, we used two different distributions. We used Gaussian distribution and we used uniform distribution. What you can see here in the table is that when we train and test with the same distribution, we have the smallest errors. But then when you train with one type of distribution, you test with another type of distribution, your errors are getting higher. The problem is to know what kind of distribution you have of your uncertainty of your span length in the field. So the key takeaway of this presentation is that we demonstrated the importance of the feature selections when building a training and testing data set. We also show that looking at only one performance metric can be detrimental. For example, we show that if you're looking only at the root mean square error, this will not grasp the harmful impact of biased training data set on some feature selections. We also highlight the importance of the uniformity of the training set in terms of the selected features. And we evaluated the impact of the uncertainty on the input parameters. So these are the list of references that I show with the first slide. So thank you for your attention.